Welcome to MAT 307 numerical analysis class. In this lecture, we are gonna introduce numerical differentiation. Uh, the derivative of a function fx at a point x equals x naught is defined by this limit. So if this limit exists, we say the derivative of function f at x naught exists, and the value of the limit will be the value of the derivative. So if we use this formula for small enough h values, this formula will give us an approximation to the numerical derivative of fx at x equals x naught. So this is an observation we can make immediately. Similarly, the derivative at the point x equals x naught can be defined by approaching from either sides, from the left or right. So this is also an equivalent formula for the derivative. So if we use this formulation and say still we have small enough h values, then this approximation will still give us an approximation for the derivative of f at x equals x naught. So as can be seen from the last two approaches, convergence to numerical derivative doesn't occur with a single formula. So we have found two formulas immediately. So two different formulas. So it seems like numerical derivative can be found by various formulas. It's not just limited to just one formula like here, this one or that one. So we have more than one options to find numerical derivative. So we can use Taylor series expansion of the function fx to further generalize these formulas. In the most general sense, if we recall our knowledge on the Taylor series expansion, the function f of x can be expanded around the point x naught as in this formulation. So fx is equal to the value of f at x naught times, plus x minus x naught times the first derivative divided by 1 factorial plus x minus x naught squared divided by the second derivative at x naught divided by 2 factorial. And if we continue like that, the general term will be like x minus x naught to the n divided by the nth derivative of f at x naught divided by n factorial. And this will continue like that. If we substitute h is equal to x minus x naught in this formulation, then we see x x naught plus h is equal to fx naught plus h times the first derivative of f at x naught divided by 1 factorial and the second derivative of x naught divided by 2 factorial times h squared and so on. And in general, we will have h to the n times the nth derivative of f at x naught divided by n factorial, and it will continue like that. Okay, according to the Taylor's remainder theorem, if we truncate this series from any term, the error of the remaining part will correspond to the value at the next expression in this range. Okay, if we, for example, truncate this series from this point on, then the error here will be like h squared times the second derivative of f at some point in this interval divided by 2 factorial. Okay, for example, if we truncate our series from this point on, okay, so if we truncate from that point on, then this will be, the error will be like h to the n plus first times the n plus first derivative of f at x at some point in this interval divided by n plus 1 factorial. So this is something we know from the Taylor's remainder theorem. Okay, if we consider this approximation, if we truncate this series from that point on, okay, so we only consider this first two terms, then the error in this approximation will be like h squared times the second derivative of f at some point c divided by 2 factorial, and this c is indeed some number within this interval. Okay, we don't have any idea about what the c is, but we know it is here. Okay, substituting this error back in the approximation, we get an exact equality because we know the error in this formulation is this much. If we substitute this value back in the formulation, then we will have an exact equality. Okay, so this part will be an approximation, but the error will compensate for the rest of the terms, and this will be equality. If we solve for the first derivative in this inequality, then we will obtain the first derivative of f at x naught is equal to this formula. Okay, so this is something we can obtain from this equation. Okay, so we solve for the first derivative here, and we obtain this equality. Then we give a definition, the forward difference formula for the first derivative. The first derivative can be approximated by this formulation. So x, the function value at x naught plus h minus the function value at x naught divided by h, and this will be an approximation to the derivative, and the error due to this approximation will be like h times the second derivative at some point c divided by 2 factorial, because we know this term will correspond to our error if we truncate this equality from here. Okay, so if we assume this is our approximation, then this will be our error, and the error will be like h times some constant given the function has second derivative and the second derivative is bounded. Okay, similarly, if we substitute h is equal to x naught minus x in the Taylor series expansion, then f x naught minus h will be expanded with this formula. Okay, if we truncate this series after the second term, so this is the 1 to the second term, and if we truncate the series from this point on, then we will have this equality, right? Because the rest of the terms, the error due to this truncation will be like this quantity, and this will be an equality. Okay, if we again solve for the first derivative here, then we obtain this formulation. Okay, this will give us the second definition, backward difference formula. The first derivative at x naught is approximated by the function value of f at x naught minus the function value of f at x naught minus h divided by h, and this approximation is a derivative approximation for the, of course, first derivative, and the error with this this formulation will be like h times the second derivative of f at some point c divided by 2 factorial. Okay, some theorem. The error due to forward and backward difference formula. If we let the function f be twice continuously differentiable function, and also let the second derivative attain its maximum value m on the interval x naught to x naught plus h, so then we say the maximum value of the second derivative is within this interval is equal to m. Then we say the second derivative of c is less than or equal to m, because m is the maximum value and c is in this interval. So for all c in this interval, it will be like less than or equal to m. This maximum will give us this observation already, and hence the error due to forward difference formula has an upper bound, like error was equal to h times the second derivative of f at some point c divided by 2. If this is bounded by m, then we say h times m over 2 is an upper bound for the error. Similarly, we can follow the same idea and say instead of the interval x naught to x naught plus h, we consider x naught minus h to x naught, and we say the maximum value on this interval is equal to m. If that happens, then we say also backward difference formula has an upper bound like that, and the upper bound will be identical, given that the m is the maximum value of the second derivative on the interval x naught minus h to x naught. Okay, so there is a remark here. If we know the maximum value of the second derivative of the function on the interval, or if we can get an idea, or if we have an approximation to the second derivative, then we say we can control the error by scaling h value. Okay, so if we have an idea about what m is, then we can modify h to obtain desired error. Okay, so if we have tolerance, like for example 10 to the negative 6, and m is, for example, like maybe 0.1, okay, then we can solve this inequality for h to obtain the optimal h value that will give us the desired tolerance, the desired accuracy. Okay, so in this case, this will be 10 to the negative 6 divided by the 10 divided by 0.1. This will be 10 to the negative 5 divided by times 2. So we can choose h greater than h less than, for example, 10 to the negative 6, and this will give us around 10 to the negative 6, and this will give us the desired accuracy. Okay, now let us consider consider both series expansion at the same time. So this was the first Taylor series expansion, and this was the second. And if we consider them at the same time, and if we subtract the second series, this one, from the first one, then we obtain like we obtain this minus that is equal to this minus that. This will cancel out, and here we will have 2h times the first derivative at x naught, and here these two terms will also cancel out, and here we will have twice h cube times this quantity. Okay, and the rest will also, this will cancel out, but we don't care about that. Okay, so once we do that, we will obtain this formulation, and we say if we truncate this from the, for example, third term, okay, so 1, 2, 3, fourth term, if we only consider the three terms, the fourth term will be our error. So we say the value of this fourth term at some point c will give us the error. So here, if we solve this equation for the first derivative of f at x naught, then this will give us this formulation. Okay, f naught, the derivative of f at x naught will be equal to this, and this will be our f. Okay, the definition for the central difference formula, this is also known as central difference formula. The first derivative of f at x naught is approximated by this formulation, and its accuracy is h squared times the third derivative of f at some point c divided by 3 factorial. Okay, and this point c has to be within x naught minus h to x naught plus h. Okay, some theorem for the accuracy of the central difference formula for an error bound. Let the function f be 3 times the continuously differentiable function. Also, let the third derivative attain its maximum value m on the interval. So here on this interval, it will attain its maximum value m. Then we say m is equal to the maximum value of the third derivative on this interval. Then we say for some c, for all c values in this interval, the second derivative will be less than or equal to m, because m is the maximum value. So the error due to the central difference formula can be rewritten as or bound can be found to be bounded by this quantity, because error is equal to h squared times the third derivative of function at c divided by 3 factorial, and we know this is less than m, so the error will be h squared divided by h squared times m divided by 3 factorial. Okay, so this will be an upper bound for error. Again, if we know the maximum value of the third derivative, we can use this information to control our error, and we can modify h values to obtain desired accuracy. Okay, some remark. The error due to forward and backward difference formula is given by some constant, because it is really a constant. It is the second derivative at some point will be a constant divided by 2, still a constant. And it is a constant times a small number h. Okay, we say h is a small number. This was the first assumption we made. While it's some constant times h squared for the central difference formula. If we go back to errors, here the backward difference formula, for example, has h times constant accuracy, and here forward difference will be h times constant again. But in the central difference formula, for example, we have constant times h squared instead. Okay, so let's go back to this point. It says the error with the central difference formula is some constant times h squared. If we neglect the constants and compare the numbers h and h squared, we observe that h squared is less than h for any number h between 0 and 1 and close to 0. So if we choose h to be close to 0, then this means h squared is much less than h. So the error due to central difference formula will be much less than the error caused by forward or backward difference formulas. Okay, so because it has h squared, and h squared will be much smaller if you're in this interval. Technically, the error due to the forward and backward difference formula is said to be order h, first order of accuracy, while it is order h squared, the second order of accuracy with the central difference formula. This means the order h means if you reduce the h value to its half, then the error will be halved. But in the central difference formula, if we take the half of h values, then the error will be 1/4 of the original error. Okay, an example. Find the forward, backward, and central difference approximation of the derivative. This is a simple derivative, and we can also take this derivative analytically, but this is just for illustration, so we will also check the accuracies with this derivative. So this is the function will be an x cube cubic function. And we are taking the derivative, we will find the numerical derivatives at x naught equals 1, and we take h is equal to 0.1 and h is equal to 0.05. Okay, so we have two h values, and we compare the absolute errors and upper bounds of errors for each h values. Let's first start with h is equal to 0.1. Then the forward difference formula will be like the function, the derivative value of f at 1 will be approximated by this formula. So if we substitute 0.1 for h, then this will be f 1.1. If we take the cube of this number, then it will be this quantity, and 1 cube will be 1 divided by h itself, so 0.1. So this will be 3.31. With the backward difference formula, this will be like f1 minus f.9 divided by 0.1, so this will be equal to that. And with the central difference formula, this will be f of 1.1 minus f of 0.9 divided by 0.2, and this will give us 3.01. If we redo our computations with h is equal to 0.05, then we will obtain this approximation for the derivative, and with the forward difference formula, then this will give us this quantity for the derivative, and with the backward difference formula we have this quantity, and central difference will give us this quantity. Okay, so I suggest you to pause the video and do these computations on your own. This is kind of important for your improvement in the subject. Okay, so the exact value of the derivative of the function f at x naught equals 1 is needed for the accuracy analysis, because we need to compare our numerical derivatives with the exact value to see what the error are. So the derivative of f at x naught equals 1 will be 3x squared, and this means f naught at 1 is equal to 3. Okay, so if we compare, if we take the absolute value of the difference between the numerical derivative and the exact derivative, then this will be like 0.31. So here this was 3.31. So if you subtract this from 3, then this will be 0.31 in absolute value. And here this will be 0.29, and this will be 0.1. Okay, we put all these values on the table, and also we do the same thing for the h equals 0.05, and this will also give us these errors. Okay, so now let's compare our errors. If we have h is equal to 0.1, the error will be 0.31, and if we take its half for h, then the error will be approximately its half, right? So the error is halved. If we again do the same thing for backward difference formula, error was 0.29, and choosing h equals to the half of the original h, then the error will be halved as well. So this is approximately the half of this quantity. Okay, what happens with the central difference formula? So this is the error with h equals 0.1, and this will be the error with h equals 0.05. So if we take the half of h, then the error will be 1/4 of the original error. So this is this is something we expect, because we know central difference formula is second order accurate formulation. Okay, and also let's check the upper bounds for the errors. We need the second and third derivatives of x cubed to approximate the upper bounds for the errors. So the second derivative will be 6x, and the third derivative will be 6. Okay, so forward difference formula, the upper bound was m times h divided by 2. So what is m? M is the maximum value of the second derivative in the interval 1 to 1.1. And we know we can indeed observe that the maximum value of the second derivative will be attained at x equals 0.1, x equals 1.1. If we substitute 1.1 here, this will be 6.6, and 6.6 times h divided by 2 will give us an upper bound for the error. Similarly, for the backward difference formula, we have the maximum value of the second derivative on the interval 0.9 to 1, and we know if we choose x equals 1, the second derivative will take its maximum value. So if we choose 1 for x, then the maximum value will be 6. 6 times h divided by 2 will give us an upper bound for the error like 0.3. And for the central difference formula, we need to go to the third derivative. The maximum value of the third derivative in the interval 0.9 to 1.1 times h squared divided by 6 will give us an upper bound for the error. So 6 is from the third derivative, the maximum value of the third derivative because it's constant and it's 6 everywhere, so the maximum value will be 6. 6 times h squared divided by 6 will give us 0.01 for the upper bound of the error. Similarly, we can do the same computations for 0.05. If we just do this for the forward difference formula, the maximum value of the second derivative at on the interval from 1 to 1.05 can be attained at x equals 1.05. If we substitute 1.05 here, then this will be the maximum value will be 6.3 times h divided by 2 will give us an upper bound for the error. Okay, these are the upper bounds for the errors, and these are the also errors. So if we compare these errors with the upper bounds, we need to observe that the errors are less than the upper bounds or equal. So this is what we expect. What we know about the upper bound for the error will be 0.335, but here we have 0.31 for the error. So the error is less than the upper bound of its value. Okay, and here this is 0.3 for the upper bound, and what we observed was 0.29, and here the upper bound was 1.01, and the error itself is 1.01. So error cannot be beyond this quantity. You can do the same. You can also observe the same fashion in the h equals 0.05 values. So you need to compare them. And a remark, as can be seen from the tables, the reduction of h values by half cuts the error caused by the forward and backward difference formula by half. This is something we mentioned earlier. And also in the central difference formula, the error is 1/4 when h is reduced to its half. This computation results numerically verify our theoretical findings because we theoretically said the forward and backward difference formula are a first order of accuracy, so they all cause if we reduce h to its half, then the error will be halved. And here in the central difference formula, if we reduce h to its half, then the error will be its 1/4. So this is these are their accuracies. That's all for this lecture. Thanks for watching carefully. Bye.